Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So our next speaker is William Stein from the University of Washington, and he'll be telling us about elliptic curves in SAGE.
All right, thank you. And I want to thank the organizers, except for me. I'm one of the organizers. But all the other organizers, thank you for doing a tremendous amount of work. And also the scientific committee. And of course, thanks the most to all the people who came, who are really what make the workshop possible, and the other speakers. So I'll be talking about elliptic curves in SAGE. This will be a fairly straightforward talk. There's a piece of software. It can compute with elliptic curves. I'll tell you a little bit about what sort of calculations it can do, a little bit about why it can do them, and then give you a demo of it doing some of these calculations. So my talk is basically in three parts. First, a brief description of the SAGE project itself, which has the description will not be focused at all on elliptic curves. Second, a kind of overview of the functionality related to elliptic curves that's in SAGE. And then finally, a demo of using SAGE to compute some things with elliptic curves. By the way, if you go to this website, wstein.org/talks, you can download the PDF of this talk and also the SAGE worksheet. And if you go to this website, you can see the SAGE worksheet for the demo and even try it out yourself live if you want via a web browser. So what is SAGE? It's a project that I started at the beginning of 2005. And it's basically a free open source mathematical software project. And it's not focused on number theory or cryptography. In particular, it's a very general project. It addresses really all areas of mathematics, including statistics. So for example, R, which is a famous open source statistics program, is one of the components of SAGE. SAGE is built up out of a wide range of open source mathematical software, such as R, Python, NumPy, SciPy. There's all kinds of numerical components. And then there are other more symbolic components of SAGE, such as singular, gap, peri, and so on. And you kind of take all this stuff together, and then you add a few 100,000 lines of code by various people over the last 5 years, and then that gives you SAGE. That's what SAGE is. There's a website which you can go to, sagemath.org. Just to show it to you briefly, I'll click on the link. Here's the website. And you can see it's just kind of a standard website. And you can look around. You can read about various aspects of SAGE. There's documentation, lots and lots of documentation. You can try SAGE online. There's tours. There's a library which lists, for example, publications. This is a nice thing to look at. These are articles that use SAGE in some way. And you can see that there are quite a few at this point. If you ever write an article that uses SAGE, go to the bottom of this page and you'll see how to cite SAGE, and that you should send an email to us so that we know to add your article to this list. So that's the SAGE website. There's really a large amount of content there. There are wikis. There's a link to an IRC chat room. There's a bug tracker. There's lists of features that we want, lists of bugs that we know about and haven't solved and have solved, and so on. SAGE itself has hundreds of contributors and thousands of users. There's, of course, a big overlap between contributors and users. But sometimes there are some people that only contribute. But as far as I can tell, they never use SAGE at all. There are other people that use SAGE, but they never contribute anything back. So you have both groups of people. And I think probably the biggest number of users are undergraduates in calculus courses and that sort of thing, just as far as raw numbers go. There's a graphical user interface. You'll see that when I do the demo a little bit later in the talk. And the code that goes into SAGE, at least the new Python code and Python code, that's the language that most of the new code is written in, that's all peer-reviewed. So as it goes into SAGE, somebody will look at it and see whether they think it's right. They'll read through it, make sure it has lots of comments, that there are lots of tests. And assuming it's up to snuff, then they will sign off on the code. So code doesn't go in until it's signed off on. This isn't perfect, just like reviewing in refereed journals isn't perfect. Not every refereed paper is correct, but it helps a lot as far as keeping the quality of code up. And the main user language of SAGE is Python. Python is a mainstream interpreter, and that's the main language you use when you interact with SAGE with a few small modifications. This is actually a huge difference or distinction between SAGE and all other essentially all other math software out there, such as Maple or Mathematica or Magma or any of these other systems. Sage uses a standard mainstream language that's supported by and written by kind of mainstream programmers. Python, for example, is heavily supported by Google, and the main person behind Python works there. So it's very much not a math-only language. So that's some of the ways in which Sage is different than many other projects. Also, the funding model for Sage, which I'll say a little bit more about in a moment, isn't commercial. It's much more grant-oriented, more academic in flavor. OK, saying more about that. So who funds Sage? So far, we've had nearly 30 workshops. The last one was Sage Days 25 in India, and that was funded by the Indian government. And the next one will be Sage Days 26, which is called Women in Sage, which will be this December, which is being funded by Microsoft Research and Justin Walker, who's sort of a private guy who is retired from working at Apple and wanted to support Sage development. But there have been many, many of these workshops. A great deal of Sage development, also just mathematical research, has gone on at these workshops over the years. For example, David Harvey right there has been to several, and he'll be speaking later today, possibly about things that he at least thought of at some point, partly at Sage workshops. And they're different. They're not just a bunch of talks. Usually there are very few talks, and as much coding as possible happens day and night at these workshops. And often we've rented out big mansions in the Seattle area and just code for days at these places. So there's been funding from companies. The main two companies are Microsoft Research right here and Google. Government agencies such as the Department of Defense and the NSF. And this is really the biggest amount of funding has come from the government. And very recently, we now have 3 new grants, 1 from DoD and 2 from NSF that will help fund Sage for the next couple of years. So things are looking very good from a funding point of view. Then there's some institutes, basically all the institutes, most of the institutes you can think of, we've had 1 or 2 or more Sage Days workshops at. For example, we've had 2 at MSRI, 2 summer graduate student workshops. The most recent one was on elliptic curves. He's wearing the t-shirt for it, which he designed for that workshop. It was like 50 graduate students all working on Sage development related to computing with elliptic curves. So that was really fun. And the Clay Math Institutes funded 2 workshops of a more scientific nature, mostly on computing with elliptic curves as well. And then IPAM at UCLA has had some workshops, and IMA wants to run a workshop. They said they'd fund one if we can come up with a timetable. And AIM's been pretty involved in Sage and so on. And there have been places in Europe, a couple of places in Europe have funded workshops, like in Barcelona and so on. So that's how Sage is funded. And presently, there's no kind of commercial company or anything selling support for Sage. It's very much a academic grassroots type project. It's all free and open source. As far as contributors go, they're all over the world. It looks like I zoomed a little too much in on the map, but there are people in far places, not just Europe and the US. One key thing to note about this map is there's a lot of developers in Europe. It's maybe even roughly equal between Europe and the United States. But there are also people in like Uruguay and Iceland and various places in Asia like Korea and so on. And I think there's somebody in South Africa, but it's missing from here. Maybe a few people. OK, so now on to the second part of the talk. So I'm going to give you an overview of functionality for computing with elliptic curves. Really basically a list. I'll divide it into a couple of parts. First, elliptic curves over the rational numbers. Then elliptic curves over finite fields. And finally, elliptic curves over number fields. And I'll just kind of give a list of capabilities and say something about each. And then when I'm finished with that, I'll then demo some of these live. And essentially everything I'll show you, I think actually everything I'll show you is standard, included in every copy of Sage. And the demo that I'll do, I just took a plain vanilla Sage 4.5.3, the latest release version of Sage, extracted it, and that's what I'm running the demo in. So there's nothing, I'm not using a whole bunch of special capabilities. I'm not using capabilities that are in software that you have to get optionally. I'm not using, Sage isn't secretly calling out to Mathematica to do things. It's all stuff included in Sage when I talk about capabilities. There's much more that you could do if you were to allow kind of everything you could do from the Sage prompt, allowing for the capability of Sage to talk to other computer algebra systems. One of the unusual things about Sage compared to the other math software systems is that because we built it partly out of Gap and Singular and Paris, we ended up writing a lot of code so that Sage could talk to other computer algebra systems. And it's not restricted to just the systems that are included in Sage. You can talk to Magma and Mathematica and so on, all from within Sage. So from that point of view, Sage can kind of do a huge amount. But that's not what I'm talking about here. I'm talking about things that you get for free. By the way, there's a reference manual that's very large, but it has a section or a chapter on that covers elliptic curves. And if you click here, we'll see it. And here it is. So this is about elliptic and plane curves. And this has more details about, or far more details about a lot of the things I'll be talking about today. So for example, if you get really interested in the P-adic L functions capabilities in SAGE for elliptic curves, you can go to this page and then start reading, and you'll learn about some of the capabilities for computing with P-adic L functions related to elliptic curves here. So, and this just gives you, a quick sense of the kind of scope of SAGE. So as far as the capabilities I'm going to show you, basically I thought about what I personally know about regarding each of these areas or have had some involvement with. So I'm sure that it's not a comprehensive list, but at least it'll be a comprehensible list. Also, another thing is there's lots of code that's been written fixing bugs, cleaning things up, making things faster. That's available on what's called the track server right here. I'll click on that link. And this is just one example. This code is not in SAGE yet. It's sitting there waiting to be included in SAGE. This particular one is so when I was preparing this talk, I think I found an issue with complex elliptic. Actually, no, this is clearly older, but it's been influenced by this talk. But John Cremona wrote a paper about computing elliptic logarithms, and together with somebody else, he's implemented an algorithm for computing elliptic logarithms over number fields. And this is code that's related to that. And you'll see that it says needs review at the top. So what he did was he created this ticket describing what he was implementing. He attached some code. He mentions that, by the way, there's some other code that this depends on. It all needs to be reviewed. And here's the actual code, which one can click on, and you'll see the code. This is SAGE code, written by John Cremona. It's actually a patch. It changes SAGE. And then if you look here, you'll see comments about it. So far, it looks like only Cremona has commented, but somebody else really needs to look at this and review it so that it can get put into SAGE. So maybe tonight or tomorrow, I'll sit there and look carefully at this, see if it makes sense, maybe look at the paper that's relevant or something, and then I'll mark it as positive review, and then the release manager. So the way SAGE releases are made, there's a release manager. The kind of release manager hat rotates around. Sometimes I'm the release manager. Sometimes, one of my grad students is a release manager. Sometimes, so currently the release manager is a guy, Matish Patel, who lives in, I think, Houston, Texas, who I've never met. But he, spends a lot of time working on SAGE, and he's very good at it, very good at programming. So he's putting together the current release. The next release manager will be, I think, a postdoc in Belgium who was at one of the SAGE days that we ran in Holland this summer, and who got extremely excited about SAGE. And so he'll be doing the next release. So it kind of rotates around the world and around people. And this is really good because anytime one person does a SAGE release, which can take about a month, that person could keep the SAGE project going in case several other people disappear, which is really important. OK, back to our talk. So now I'm going to talk about elliptic curves over Q. But before I do that, I want to emphasize that most of the capabilities for computing with elliptic curves over Q have been their implementation has been motivated by this conjecture of Birch and Swinnerton-Dyer, which is really, of course, one of the driving forces in modern arithmetic geometry. And the main people, really, I think, who have written a lot of code in SAGE for computing things about this conjecture are Robert Miller and Robert Bradshaw, two of my recent PhD students who have both graduated, Chris Wuthruck, who's in Nottingham, and John Cremona, and also me. And really, the project started initially with a summer project I ran, which was about verifying the full conjecture, this statement right here, for all elliptic curves up to conductor 1000, except the curves of rank 2, for which it's an open problem to even give an algorithm that will verify this conjecture. There are 18 curves that have to be omitted, but for several thousand curves of conductor up to 1000, we wanted to verify this conjecture, and we started putting together various bits of code in Python to organize our work, and that's really the very beginnings of SAGE. So this explicit verification of this conjecture in specific cases is the original motivating problem for this SAGE software. And by the way, an application of SAGE is verification of the full conjecture for a very large number of curves of conductor up to 5,000. There's a new paper by Robert Miller, which I'm not sure if it's on the archive yet. I think it is, which is about this problem. So it is on the archive, yes. So if you want to look at this, it's kind of neat. I think I've been told that a couple of years ago, it was strange in that people had computed all the quantities appearing here except the order of Shaw in many cases, but there are a lot of cases where you didn't know the exact order of Shaw. So even 11a, somehow nobody had just gone through and very carefully figured out exactly what the order of Shaw is by combining various theorems. And it was kind of silly that this hadn't been done yet. So now there are a couple of papers, and there's a lot of work in this direction. I think you started pointing this out to various people, and then John heard about it, and then he told me I should do something, and that's how this got started. But in any case, it's going pretty well. And it's kind of a neat problem because you go up to 1,000 and you'll have a couple of exceptional curves where tricky things happen. Then you go up to 2,000 and there'll be new exceptional curves for which different tricky things happen. And you have to keep refining your techniques to be able, all amounts to computing the conjectural order, or it's not the conjectural. You compute the conjectural order of Shaw, you get 1, and now you want to prove that the Shaffer-Tate group has order 1. And you have to assemble together various theorems to prove that. Okay, so now on to functionality, much of which, again, is motivated. It just looks like a big list of capabilities, and BSD isn't explicitly really mentioned anywhere on this slide, but in a sense, almost everything here is motivated by trying to compute the quantities appearing in that conjecture. In particular, the order of Shaw. Not just the conjectural order, but the actual order of Shaw. That's one of the main motivations for a lot of this. Okay, so the sorts of things Sage can compute for elliptic curves over Q. It can compute standard invariants like the conductor, Tamagawa numbers, and so on. This mainly relies on Paris. The Paris/GP interpreter is in Sage, and it's also usable as a C library. Sage uses it as a C library for efficiency purposes, and that gives it the ability to compute some of these things. As we'll see in a moment, there is also a complete implementation of Tate's algorithm over number fields, and that can alternatively be used to compute these quantities. And that's a new implementation only in Sage. That's not in Paris. Other capabilities, so you can compute Mordell-Weil groups and do point searches, and of course then get regulators. You can compute Mordell-Weil groups, one using MW rank, which is tightly integrated into Sage now. And two, you can also use a Paris program of Denis Simon, also tightly integrated into Sage for doing two descents. And they do two descents in two very different ways. So in some cases, Cremona's program is much better. In other cases, Denis Simon's program is much better. Another nice thing about Denis Simon's program is that it also works over number fields. So you can compute Mordell-Weil groups. You can compute S integral points for S the empty set or S not the empty set. And this is nice to have available in a free open source package. It wasn't available until recently in any free open source code, but it now is. And this is new code. So two master's students, Nagel and Martis in Germany, wrote the initial code. Cremona refereed it and ended up having to do a lot of work on it in the refereeing process. And then I refereed what Cremona refereed because he had changed so many things. And my refereeing was mainly run Magma's S integral points or integral points command and compare it to the output of Sage. And they were just like all kinds of differences. And so I just ran them and discovered many bugs in Magma and many bugs in Sage's not implemented things. So we ended up sending Magma a list of all the ones where their curves, all the examples where they got wrong answers. And I also sent a list to the people writing this patch. And then they both did work. And now my understanding is that they agree in the latest versions. Yeah?
Magma was missing points or putting bogus points in?
Missing points. You never put bogus points in. Good point. Because you can easily check. Sorry. Thanks for the clarification. Yeah, the hard part's missing points because you don't search far enough and so on. And it's an algorithm assuming you can compute the Mordell-Weil group. Once you have the Mordell-Weil group, then there's an algorithmic way to do this. And it's really fast. Given the assumptions about having computed the Mordell-Weil group, it's pretty good. You can also compute with complex L series. So when you can evaluate, basically you compute the Taylor series of the L function of elliptic curve at any point to any number of terms. And you can also compute the zeros, many of them very quickly in the critical strip. So this combines work of Dachitzer and Mike Rubenstein, two completely separate kind of views on computing with complex L functions. But there's a nice simple interface to it in Sage, which I'll demo in a moment. There's lots of code for computing with P-adic L functions and P-adic heights. So this code see, for computing with p-adic heights is originally motivated mainly by questions of Barry Mazur in trying to study what he calls the shadow lines associated to, well, I don't want to go into details about that at all, but some questions of Barry Mazur related to Heegner points and so on. And the p-adic L functions codes, all written, I guess, by me and Christian Wetherick, mainly Chris Wetherick, and that's all about applying theorems in Iwasawa theory to computing information about Mordell-Weil and Schaff-Rayleigh Tate groups. That's what the motivation is. And he's implemented this stuff in lots of subtle cases, like for supersingular curves and so on, and really optimized it. For example, modular symbols happen to be a key. Computing modular symbols efficiently is a key part of computing these p-adic L functions. And Dosage has its own complete general modular symbols package that I wrote and other people have improved. If you just want to compute modular symbols where it's gamma 0 of n and weight 2, then Cremona's C++ library is much faster. And so for this application, Cremona's C++ library is used for computing elliptic curve p-adic L functions. So there's been a lot of work put into that. And that's really, really critical for being able to compute information about Schaff-Rayleigh Tate groups. And coming next to Schaff-Rayleigh Tate groups, so you can compute their conjectural order, of course, assuming, for rank greater than or equal to 4, you can compute it to some number of digits. And you can compute the actual order in many cases, which is pretty neat. And it's really motivated by kind of a theoretical question, BSD. There's lots of code for computing with Heegner points, and also very uniquely, there's new code for computing information about Colley-Vaughan's Euler system of Heegner points, especially in the case of curves of rank 2, 3, and so on. So we've applied this code, me, Jared Weinstein, and Jen Balakrishnan, to verify Colley-Vaughan's conjecture that his Colley-Vaughan classes, his cohomology classes, are non-zero for some curves of rank 2 and 3, which is pretty recent. This hasn't appeared in a paper yet, but we came up with an algorithm and implemented it. And I think as of a few days ago, finally proved it's really correct. And so you can actually do calculations. You could figure out what the Colley-Vaughan classes are. You can figure out which ones are non-zero. Once you know that one of them is non-zero, by working out for a couple of weeks the details of a remark that Carl Rubin made, you can that builds on work of Ben Howard, you can figure out what all the other Colley-Vaughan classes are up to scalars and so on. So it's pretty neat to be able to kind of really get your hands on Colley-Vaughan's Euler system, especially in the case of curves of rank greater than 1, which is something that I got really interested in due to work of Christophe Cornu about 10 years ago when he proved Mazur's conjecture. Enumeration of all curves of given conductors. So Cremona wrote these big C++ programs that did this, that he used to make his tables up to conductor 130,000. Technically, they're in Sage, so I'm putting them here. However, there isn't just a command in Sage that you run that gives you the output, the list of curves of a given conductor. It's feasible that somebody could write such a thing. It just hasn't been done. The code's in there, but it's not exposed to the user in an easy way yet. So it's a little ad to get somebody to do that. Enumeration of the isogeny class of a curve, computation of division polynomials. So there's basically a whole bunch of different variants because different people wanted to use division polynomials for different applications. And so there's lots of different options when you ask for a division polynomial and different things you can do. I remember that I think the first version just was some very slow, naive implementation that was good if you really wanted it as a polynomial, but what if you wanted the polynomial with some value substituted in? So David Cole had implemented the first version long ago, but David Harvey wanted it with some value substituted in, so he kind of rewrote it so it could do that. And things sort of developed over the years as a result of this. There's code for computing images of Galois. So for example, if you have an elliptic curve and you want to know all primes for which the representation is not surjective, the mod P representation is not surjective, you can just ask. There's a command that will give you that. This is important because it's a hypothesis to Cato's theorem bounding orders of Schaff-Rayleigh Tate groups. So there's information about images of Galois. You can get much more precise information from a really nice program of Drew Sutherland, who's sitting right here. But this is in gray because I've written code that makes it so you can use it in Sage. I've included it in Sage, but it hasn't actually got into Sage because of the referee process. So it's in referee. Actually, what happened was I wrote the code. I posted it. Somebody else said, hey, this breaks something weird somewhere else in Sage. I don't understand this. Needs work. And then I haven't looked at it since. So it's like when you write a paper and you submit it, and then the referee gives you back some comments, and you're like, oh, I don't even want to look at this. And then, and then you like put it in your drawer, and then the editor hopefully eventually reminds you should look at it a couple of months later, or they're going to drop it from the journal. So that's the situation with this code right now. But I will get around to it. So yeah, Sage is a lot like peer-reviewed journals with all the problems that they have. Isogenies and isomorphism. So Dan Chameau, I don't know if he's in the crowd here because he works here at Microsoft, but he was a student at UW and he wrote a bunch of code for computing with isogenies as a final project, and it's been refined. You can, given two curves, you can ask for an explicit isomorphism from one to the other if it exists, etc. There's some code, a big GP program, or maybe a small one, I don't remember, by Carl Rubin and Alice Silverberg that's included in Sage. And so there's a command in Sage. If you have an elliptic curve, you can ask for other elliptic curves with the same mod 5 representation. The curves with a very big conductor, but you can at least ask for them, and it will systematically give you the family of such curves. And I think there'll be a talk about a related family later in this ECC. And of course, there's code for plotting elliptic curves. Okay, elliptic curves over finite fields. This is I think, a lot of functionality that was mentioned in some of the talks yesterday. So point counting and group structure. So if you have any finite field at all, and you're willing to wait a while, if it's a huge finite field, doesn't have to be FP, but FQ is fine, then you can count the number of points and compute the exact group structure. There's an implementation by John Cremona of baby step, giant step algorithm that allows you to get the exact structure. So this is good, especially if the field isn't too big. There's also fast point counting. So in like a minute, you can find, if you have an elliptic curve over Q, you can find all the a sub p, that is the point counts mod p, for all p up to about 10 to the 7th. So you can do that in a very reasonable amount of time. This really just directly calls the AP list command in the Perry C library, which is, as far as I know, the fastest implementation of this. And if you look in the source code, it has a whole bunch of different cases depending on whether your curve has CM or not, depending on whether the prime is at most 97, at most 460, whatever, at most something else. It switches between algorithms depending on P. So just advertising that, also available in Perry. There's the SEA algorithm, and it's, I think, again, a very good implementation that is inherited from Perry, that's in Sage, which you can just use. There's computation of the vapouring, isogeny, and isomorphisms again. The mainstream method of graphs, which allows you to enumerate all the supersingular J invariants and characteristic P, and also compute the P isogeny graph, the L isogeny graph for small l, like 2, 3, 5, 7, and so on. You can also do computation with Eichler orders, so you can make a rational quaternion algebra ramified at, say, P in infinity, consider an Eichler order of level n in there, and then enumerate the right ideal classes, and then compute the action of the Heck operators on the free abelian group on the right ideal classes, check equivalence, et cetera, et cetera. So this is a very important algorithm. It's an alternative way of getting information about modular forms. It also plays a role in cryptography, in constructing what are called expander graphs. I think there's some hash function or something that Kristen did some work on that basically involves this construction. I actually got into using Magma a lot in about 1998 because of David Cole's very nice implementation of an algorithm for computing with these Eichler orders, and hopefully he'll mention something about them in his talk later today. So me and John Bobber at an Arizona Winter School about a year and a half ago spent a lot of time trying to write a really, really fast implementation of this, and I think it's pretty good. And it got sped up a lot in the referee process again by Gonzalo Ternaria, which we did as much as we could to make it fast, and then for large levels he was able to make it much, an order of magnitude faster actually, if you know the right parameters to use at least. And
algebras over Q?
Yes, this is just rational quaternion algebras. There are plans to have quaternion algebras over totally real fields, but that's not implemented yet. There have been many discussions with John Voigt, but no serious code has been written. But Ali, for example, is working on this. What?
Didn't he write some code for that? Or?
He has a kind of different approach, but yeah, he has some stuff in Magma. He doesn't have anything in Sage at all. Let's see, and then the elliptic curve factorization method is implemented. It's in Perry. If you just do the factor command in Perry, you get it, depending on your number. But there's also a program called GMP-ECM that probably several people in the audience here have been involved with and used for all kinds of cool things. Paul Zimmerman distributes it and does a lot of work on it. That program is included in Sage, and there's a nice interface to it. And you can also plot curves over finite fields, which is just amusing because they look kind of random. I had one earlier in the talk. Okay, then elliptic curves over number fields. There's less here, but this is where a lot of people are putting effort lately. So there's a complete implementation of Tate's algorithm. You can compute thus the conductor, Tamagawa numbers, and so on of an elliptic curve over a number field. Just some names of people who have put work into this. David Rowe. He actually sat down and wrote the first version. And then John Cremona went through it, and he was refereeing it, and then he ended up rewriting a lot of it. And I think he may have finally changed the variable names from what they. So basically, it all started with Richard Pinch's Modula 2 implementation or something, and the variable names kind of had stayed the same even through David Rowe's version. I think John finally changed the variable names to be a little more meaningful instead of just like little letters and stuff. So there's that nice implementation. Robert Bradshaw was doing a bunch of work in his thesis on analogs of the Gross-Zagier formula and kind of some of Kolyvag and stuff, but over ring class fields. And he really needed explicit computation of heights of points over number fields. So he implemented that, which is built on top of Tate's algorithm a little bit, and some work of Niels Bruyn and others. And there's computation of Mordell-Weil groups via this program of Denis Simon. So if you make an elliptic curve over a number field, you can just ask for it to do it. There's a command Simon 2descent. It'll compute the rank of the 2-Selmer group, and it'll do a point search. And it gives you kind of lower and upper bounds. So it's not a complete implementation of finding, but it's very useful. Yeah?
It's only a descent via 2 isogeny, I think.
Yeah, it's only 2descent.
So it's not the 2-Selmer group. It's going to be a little bigger.
Okay. Yeah, that was, yeah, okay. But you can still compute Mordell-Weil groups in some cases. But good point. Periods and elliptic logs. So this is something that's new. That's part of a project of Cremona. That so he just told me that he's very proud of this new code for computing, for example, period lattices of elliptic curves over number fields. You give any real or complex embedding of the number field, and it gives you back the period lattice, and you can compute elliptic logs and elliptic exponentials. And he was very excited about this because it's not available anywhere else, apparently. So I'm going to do a demo with the rest of my time. And if you happen to have a laptop and you want to follow along, which is probably one person, then you can go to this URL right here. Or if you want to look at this later on, because chances are I'm going to, despite trying to not to do so, I will probably accidentally let things fly by a little too much. So again, if you kind of see something, it catches your eye and you want to look at it in more detail, you can look at this and try it out. And by the way, just to advertise this a little more, if you go to demo.sagemb.org, let me log out, then you can sign up for a Sage Notebook account. What this allows you to do is use Sage over the web with any web browser. What happens after you sign up is you sign in, and then you get a list of your worksheets. You can also click on Published, and you see all the published worksheets. One of them is the worksheet for my demo that I'm about to give. And if you've signed in, you can click Edit this. You'll get actually edit a copy. You click on that, and then you'll have a complete copy of this worksheet. That's your own. Whoops, I just clicked on my email. Whoops. A link to that. But you'll get a complete copy of the worksheet, and then you can just work through it. And this is what you'll see. And this is Sage, by the way. So here's Sage. It has a graphical interface. If you don't like graphical interfaces at all, there's also a command line. Let me show you that quickly, too, just in case. Command line. OK, so there's a command line version of Sage, which is actually a very nice command line. You can go back and forth and look through your history and so on. It's actually one of the nicest command lines for a command line program. But here's Sage. You can put HTML with mathematics. If you double click on some of this HTML, it turns into a WYSIWYG editor, and then you can put math in dollar signs, etc., and click Save Changes. This is actually running over at UW, so I think I'll switch to the version that's on my laptop for the rest of the talk. OK, so now here's the demo. So first, I'm going to show you some examples of computing with elliptic curves over Q. And I have to choose a size. So somebody in the back, Alice, is this a reasonable size or is it too small? It's OK. Okay. Is that better? I feel like an eye exam. So I'll go with this size. So here's how you define an elliptic curve. It's actually exactly the same as in some other systems, like Perry and Magma. So you say elliptic curve, and then you give the A invariance. There are, in fact, many other ways to define an elliptic curve. If you want to find out about any command in Sage, you can put the cursor right after the open parentheses, and then you hit the tab key. And it'll look up the help for the command, and then you can look at it. This shows all the different ways of making an elliptic curve. So you can give 5 A invariants, or you can give 2 of them. If you can't remember which ones to give in what order, you can look at this. You can also give one of the Cremona labels. By default, all the curves up to conductor 10,000 are in Sage, included in every copy of Sage. There's an optional package you can install which gives you the curves up to conductor 130,000. And you can also explicitly specify a ring. And I guess you can get one from a J invariant. But this caused a lot of confusion, so there's another command, elliptic curve from J, which you should use. And with all Sage functions, well, not all of them, but with about 85% of them, there are examples that illustrate how to use them. And that's what you're seeing here. So this illustrates that you can create an elliptic curve from A invariants or from Cremona labels using the new Cremona labeling where it's lowercase letters. You can create them over finite fields, etc. And then when you're done with the help, you just hit escape and it goes away. So that's how you make elliptic curves over Q and how you remember the command. You can also do, if you can't remember how even the command, you can say ELL tab, and it gives you all the commands that start with ELL. So if you can't remember how to spell elliptic curve, for example, then you can just select it like that. OK, so now we have an elliptic curve. And let's transform it into minimal form. There's a show command for any object in Sage. You can say show of that object, and it will typeset it, and then display a typeset version. Notice here what I did was I just printed it out, and it's like printed out as ASCII, but you can also print it out in a typeset form. And this is not an image. This is a JS math. So it's just some special fonts that get laid out nicely using JavaScript. If you have any object in Sage, like an elliptic curve, you can say E dot, and then hit the tab key, and it gives you a list of all the functions you can call in that object. And here's a list of the functions for an elliptic curve over Q. There's quite a few. So and it goes on and on and on. So there's a couple of functions people have implemented. It always ends up getting really long, and then people divide it up. So for example, if you do e.sha, then you'll get a new object back, which is sort of an abstractly, you should think of as the Shafrevich-Tate group of the elliptic curve. And then it has methods on it that you can call. So things get kind of regathered up in that way. OK, so those are things you can do with elliptic curves. Now let's do a few things with an elliptic curve. So moving on, let's compute the discriminant. So I just did that live. The output's there, so you don't have to guess what's going to appear. Here's the conductor. And then maybe you want to factor the conductor, but you can't remember what to do. So you do n.f, hit the tab key, and you see all the methods on an integer, which are completely different than the methods on an elliptic curve. You don't have e.factor. You have e.other stuff. And then you can select factor and do that. And it gives you back the factorization of the conductor, which in this case is 11 times 941. So Tamagawa numbers, and they're both 1 at those 2 primes. You can compute the rank, the analytic rank, generators for the Mordell-Weil group.
Are these coming out of the database?
I don't know. Maybe. I think they probably are. So for commands like rank, I think there's an option. OK, so they're not. So each of these commands can use the database if you have it available. And there's an option, use database equals. If you say use database equals true, it'll try to get the data out of the database. For example, it'll try to compute the rank by looking it up in Cremona's tables. That's not on by default. And so the answer to your question is, I think, no. It's not using the database for this. So these are so when I say e.rank, what it does is it runs MW rank and then gets the rank. The analytic rank, it runs some other program that computes the order of vanishing of the L function at 1. egens, again, that was just MW rank. The regulator, probably using Paris. And then Simone 2 descent. So at this point, it actually fired up one single copy of GP. It loaded Simone's program into that one copy of GP. It then fed the curve into it, got the answer, and then recorded that, and then converted the answer back into a Sage format. You don't have to know about that, but that's what happened. This is important, though, because there are many GP scripts out there, and they don't work together. If you try to look, because GP just has one big global namespace, so if you try to combine them in the same program, hell breaks loose. However, what you can do is simply have different copies of GP running with each of those programs out there. And that's what's happening here. It's a little crazy, but it gets the job done. And his program's quite good, so it's nice to have. Also, you can say print e.mwrank. This literally just runs mwrank at the command prompt, shows you the output, and you can look at it. If you like looking at the output of mwrank, which many people do, then you have that easy option. I mentioned integral points, so you can compute the integral points or the S integral points on our curve. And this is up to sign. There's one missing, of course. But if you look at the documentation, you'll see that for each point, one of p and minus p is chosen. So if you want all the integral points, and you have to go through each one that you got and take its negative using the group law. And here's S integral points. You can also compute with the complex L series. You just say E.L series, and it gives you back an object. It used to be that E had a whole bunch of methods directly related to L series, but now what you get is a single object, and you say L.tab, and you get all the methods just relevant to computing with the L series of the elliptic curve. So you can plot it, for example, as I've done here. You can see that it vanishes at 1, which is good because the rank is 1. Looks like the order of vanishing is 1. You can evaluate it at any point you want. So here I'm evaluating it at 2 plus 3i, thanks to Tim Dotchitzer's program, which is now running in a separate copy of GP from the one that's running Denis Simone's program. You can compute the Taylor series about any point at all. So, the kind of really famous one is the Taylor series about s equal to 1. But you can also just ask for the Taylor series about 1 plus I, or whatever you want. And there it is. So this is floating point approximation to the Taylor series of the L function. Z is s minus 1 here. And down here, Z is s minus the quantity 1 plus I. You can also compute the imaginary parts of the zeros of the L function pretty quickly. And here's a plot of the first 20 of those. And notice they're a lot more densely spaced, and they appear a lot sooner than what you see for the Riemann zeta function, where you don't see even a single one until you get up to around 14. Whereas for an elliptic curve, you have a lot more of them. And for a rank 2 curve, or rank 1 curve, you have sort of one right there. So there's that one. All right, let's compute some things about a rank 4 curve. There's a little database of curves of various ranks in Sage, and I'm using it. So here, I think it actually probably knew. It seemed really quick, but whatever. Here are generators for the Mordell-Weil group. That was computed by MW-rank, getting the L series again. This takes a little time, but it computes the L series of this curve of conductor 234,446, which is presumably the smallest conductor curve of rank 4, though we don't know that for sure. There's the Taylor series. It sure looks like it vanishes to order 4. Notice that each of the coefficients up to z to the 3 is close to 0 to the precision we're computing, and then you get this first very non-zero coefficient. Unfortunately, it's an open problem to prove that the order of vanishing is in fact 4 for this case.
So it's doing a lot of point counts.
Yes. Yeah. So it's just computing a sub p for p up to some bound. Okay, there are also P-adic invariants. So a nice example of a curve to compute a bunch of P-adic stuff about is the elliptic curve 3D9a, which is the smallest conductor curve of rank 2. See, it has rank 2. Let's compute its 5-adic L series. And that's just an object you get back, and some modular symbol stuff was computed. If you then say dot series and give a precision, it will compute up to, actually, not a precision. It's a precision. So it'll compute the series as much as it can using a certain amount of information. If you replace the 3 by a 4, you get a higher precision answer, but it will take a lot longer. It kind of grows exponentially in complexity. But for most applications, you just need enough precision so that you see that some coefficient is non-zero. And for many things that you're doing, that's all you need. So for example, the fact that the 5-adic L series looks like this allows people who are familiar with results from Iwasawa theory to deduce all kinds of exciting consequences. You can also compute P-adic regulators to high precision very, very efficiently. And not just for 5. If you put a bigger number like 97, we shall see, I think, that it's very reasonable as far as the time goes. So less than a second. And this is pretty neat that it's possible to do this. So when I started Sage there was no known algorithm for computing p-adic regulators efficiently. Mazur, Tate, and me wrote a paper, I wrote a paper about this, and then David Harvey found out about it at one of these workshops I mentioned and dramatically improved the algorithm, and that's what's running right here. And I think some of what he'll talk about later today is kind of related to this, maybe. You can also ask for the Shafraevich-Tate group and compute things about it. So you can ask for its analytic order, so just its conjectural order is 1.0000. You can ask for its order according to the 5-adic analog of the Bircham-Swinnerton-Dyer conjecture that Mazur, Tate, and Teitelbaum made. And you get 1 to precision 5 squared. You can also ask, using Iwasawa theory, try to bound the p primary part of SHA. And it will say that 0 means that ord 5 of SHA is less than or equal to 0. So that's an upper bound. It's pretty neat. Using descent, you'd be very hard pressed to show that the 5 part of SHA is trivial. You'd certainly not show that the 29 part of SHA is trivial. Computing, say, the 29 Selmer group of an elliptic curve is completely infeasible, especially this one for which all the mod p representations are surjective. But in just over 2 seconds, again, using basically p-adic L series and regulators, you can compute and find that it's 0. And I ran this for a couple hours and was able to run it for all p up to 2,000, below 2,466, except there are 3 p where the elliptic curve is supersingular mod p, so you're not able to verify triviality of SHA there. One expects that SHA is trivial for this curve, as you saw above, but it's an open problem to show that. It's even an open problem to show that SHA is finite. I think it's even an open problem to show that SHA p is 0 for infinitely many p. But at least this checks it for a p up to some impressive bound. Okay, this is kind of similar. Goes into Heegner points. But I really want to say a few things about elliptic curves over finite fields. So there's lots you can do with Heegner points, images of Galois. Let's see. This is I want to show this one really quickly. So this is the mod 5 family that you get from this code of Alice Silverberg and Carl Rubin. And you can see it's really, really huge. So it's these are the coefficients, or this is a Weierstrass equation of an elliptic curve, but it's over some rational function field in T. And it's really, really big. It's most of the worksheet, actually. But you can specialize T, say, to 1, and then you get a much smaller. This didn't work because I didn't define anything above, and this is a fresh worksheet. But what you'll get is a much smaller model, and then you can compute, and you'll find that, in fact, the A invariants do match up, mod 5. And you can factor the conductor, and you find it's some multiple of the original one in this case. The original curve that we were looking at had this conductor. The other one that has the same mod 5 representation has this bigger conductor. So that's this mod 5 family code. You can also plot elliptic curves. And here's the plot that started the talk, or that was on my opening slide. So here's the curve 11A, 37A, 389A, 5077A, and 234446A. I declare it. So there they are. You can just see pictures of them. OK, moving on to elliptic curves over finite fields in my remaining 2 or 3 minutes. Here's how you define a finite field in Sage. You say Ka equals gf7 to the 6, for example. And that makes the degree 6 extension of gf7. Then you can make an elliptic curve over it and ask for its cardinality. This is running the baby step, giant step code of Cremona that I was talking about. And you can ask for the exact structure of the abelian group, which is either cyclic or a product of 2 cyclic groups. In this case, it's cyclic. You can also ask for the AP for all p up to some bound. So here's all the p up to 10 to the 6th. Here's the first view of them. This is Python notation for getting the first 10 entries of a list. Just for fun, let's look at what I just did is I drew in real time a histogram of, for each p, I took AP and divided it by 2 square root of p. And hence I got a whole bunch of numbers between -1 and 1. And then I put them in a histogram, and you get a beautiful semicircle.
So you're not a finite field here. This is global again.
Well, what I do is I took a single elliptic curve over Q, but then I reduced it mod lots of primes. So there's a finite field. There are a whole bunch of finite fields, but yeah, this is global. And this illustrates the Sato-Tate conjecture that this converges, or should I say theorem of Taylor et al., which is that for non-CM curves, you always get this. OK, at least something over a finite field so you don't get too annoyed, Renee, which is an implementation of SEA being demonstrated here. So in a little over a second, you can compute the number of points over the next prime after 10 to the 50. And this is using code that Henri Cohen told me he hired a couple of people over a summer a couple of years ago to write this in GP, or for GP. And then we included it in Sage. And strangely, until I don't think it's been released in Paris itself, even now. But I think they're about to or something, maybe in the next few months. But we included it in Sage. Here's an example. It's kind of neat because the curve is defined over an extension, but you still get the points. But the J invariant is in the base field. So John Cremona worked out all the tricks for, as long as the J invariant's in the base field, you can get the point counts over all the extensions. Okay, here's a picture of the supersingular module. So there's one little circle there for each supersingular J invariant in characteristic 389. And then this is the two isogeny graph. So every time there's a two isogeny from one of the curves to another one, there's a little arrow in that direction. And you can see it right here. And then there's a graph editor which unfortunately only, it's really nice because you can drag things around and have it live do the graph layout algorithm. Unfortunately, it doesn't preserve the directions of the arrows in the version that's in Sage. The guy who wrote it, Rado, he's a grad student somewhere. He's made it so that it works in general, but it's just not in Sage yet. But it's very nice, as you can see. There's also this Brandt modules thing, which allows you to do a similar calculation, but where you can add in some extra level structure. So I do that. And then when you draw the graph, you kind of see the extra level structure in that there's extra elliptic. I mean, it looks like the original one, but somehow the graph layout algorithm discovers the extra level structure. And you see things that are on top of each other that are related, that have similar, the same curve, but with different level structure. Okay, ECM factorization. This is the ECM command. It's GMP ECM. See, GMP ECM. And there you are. And it factors some integers. And then here's plotting an elliptic curve over a finite field. Pretty much what you'd expect. So you can see, by the way, this illustrates that Sage has an interact feature. You can put add interact before a function. It'll analyze all the inputs to the function and make it into an interactive kind of widget-controlled function. And depending on what the different inputs are, it'll make different widgets. Very much like Mathematica's manipulate command. That's a nice little feature. And you also have elliptic curves over number fields, which I'll finish with. Here's an example of the field Q root 2, an elliptic curve over Q root 2 that Lassina Dembele found after a big search. And the neat thing about this curve is it has fairly small conductor, and it has rank 2. So here, using Simone 2 descent, we find 2 independent points on the curve, and that the rank is 2. The lower and upper bounds are both 2. Here are the points. Compute their heights, and compute their regulator, compute the period lattice, and I really wish I could compute the analytic order of Shaw. That would be the nice finish for this talk, but unfortunately, that's not in Sage yet. But at least you can compute the point counts mod lots of P, but it's almost the case that you could compute the analytic order of Shaw for sort of general curves over number fields, but that's not quite available yet. Getting close. All right, and in case you're wondering, Sage does have 3D plotting, which is what I'll finish with. So what this is doing is it loads a model of Yoda and then plots it using the 3D plotting capabilities in Sage. OK, so that is my talk. Do you have any questions? Yes, Renee.
Yes, integral points.
Yes.
This is elliptic logarithm.
Yes, definitely. Yes. So Renee's question is, how does the S integral points code use elliptic linear forms and elliptic logarithms? And the answer is yes. Other questions? If there are any? Yes?
Is there a way to jump to the open source code from this interface?
Say what?
If I want to jump to the open source.
Oh, yes. So his question is, if he wants to jump to the source code for something, let's say height, all you do is you put double question mark and hit the tab key, and it gives you the source code for that function. And here it is. That's the documentation, but somewhere down there, there is the actual source code. There's the source code. Moreover, there is you can see the file name at the top right here. And if you go to that file on your computer, then you'll see the rest of the source code. So yes, you can look at the source code for any function from this interface.
But you can't edit it yet?
Nope, not yet. There's been discussions. Demos have been made by Tom Boothby and other people, but it's certainly planned that that you can just edit the Sage library through the Sage notebook. That would be great. But that hasn't happened yet. Okay, other questions? If there are any? Yes, Dan.
I was just wondering, can you put the Yoda back for a picture?
Oh, sure. I'll stop it spinning for your picture. So anything else? Any other questions? Oh, yeah, sorry.
Is there a trace capability so you'll know what code your answer depends on?
Yes, but I never use it, so I can't remember what it's called. Maybe there's a trace command, which like if you it will step line by line through the code as it's run. At least it'll step through the Python code, so that can be useful. There's a search_src command, which will search the entire source code for, I don't know, names. Like if you wonder whether there's any function called Victor Miller, then you can just do search src, and it searches the entire source code using grep, and it returns everything that has Victor Miller as a subset of it. And you can get links to this. So there's a lot of code in there. There is a command that Mike Hansen wrote, which is supposed to allow you to run a command, and it will tell you which systems are used, which you should use if you're going to cite a paper. But I can't remember at the moment what the name of that command is, which is kind of ridiculous given that the point of the command is so you remember the names of other things. And this command should tell me, but I can't remember what it is. So the answer is sort of yes. And if you write a paper or something using Sage, you're strongly encouraged to try to figure out what is being used and cite that as well. Okay, other questions if there are any? Oh, yes?
Can you just mention some other things that you think Sage doesn't do yet?
Sure.
Some things that you might find immediately.
So just a quick list. I actually made a little list here of these are things related to elliptic curves that are kind of in progress or people are working on, but they're definitely not in Sage yet. So very quickly, lots of stuff for totally real fields, like enumeration of curves. No Melkis has been working on some stuff related to this in the last few days. Doing 3 and 4 descents. I don't know if anyone's working on this over Q, but it should be in Sage, but it's not. Integral and S-integral points, but over number fields instead of over Q. L functions over number fields. That was really annoying at the end when I couldn't compute the analytic order of Shaw. L functions over function fields. So Sal, who's like right around here somewhere right there, he has a lot of code that he wrote with Chris Hall for his thesis for computing with L functions over function fields, and that should get into Sage. And they've been working on getting it into Sage. Doing 2 descents over function fields. We had a function field Sage days, and one of the project groups involved a lot of work on implementing 2 descents over function fields. Computing images of Galois. There's code of Drew Sutherland that I mentioned. This needs to get actually included in Sage. Massive tables. So we've been putting together a lot of data in queryable tables that are online, and it needs to be that there's really easy to use functions from Sage that allow you to query these tables and get the data without having to install a database locally. There's a demo here at db.modform.org, which you can look at. Pairings over finite fields. I checked, and it looked like we only have the VE pairing included in Sage standard, even though I've heard talks about people implementing other pairings in Sage, but for some reason they don't seem to actually make their way into Sage. Models, so Tanya Lang in the back has a student who's been implementing all kinds of models, but they're not in Sage yet. And I think they're going to be included in Sage soon, or at least submitted for inclusion. Working with function fields is a big gap. So you can't really make a point on a generic point on an elliptic curve and work with it, which is really annoying. And it's really basic capability that you should have, but it's not in Sage. I wrote a lot of code for function fields, but it's really not made its way into Sage yet. So that's an answer to your question. Okay. Renee?
I guess when you say integral, you mean that the x and the y coordinates are integral, right?
I guess that's what I mean.
Yeah. So, but you could also insist that another function is integral, and that also has applications.
Okay. So his question is, you could generalize the notion of S integrality, and that also has applications. And all this integral points stuff is motivated by applications. So John Cremona is very motivated by applications to enumerating all curves with given conductor. And S-integral points are an approach to that problem. So.
Do you intend to, I don't say S integral, I mean with respect to another function. So
right.
I want 1 over x to be integral.
Yeah.
You will have that, or
yeah. Future plan. Great. Yeah, as soon as you write it. Hundreds of people submit code to Sage, or your student. Okay, anything else? So, yeah, okay, great.
Let's thank William again.
Thanks.